So if you want to tell the difference between an acid and a base, you probably couldn't do it by looking at it. Like, look here. Hydrochloric acid is stomach acid. It is colorless, watery, has a pungent odor, and is corrosive. Ammonia here is a base. It is colorless, also comes in liquid, is also corrosive, and also has a strong odor. So the physical properties are pretty similar, but the chemical ones, that's where the change happens. In the Arrhenius definition of acids and bases, an acid has hydrogen in its equation, rather its formula, and forms hydronium in contact with water in an ionization reaction like this one, where hydrochloric acid comes in contact with water and creates hydronium. A base has hydroxide and forms hydroxide in contact with water, like this reaction, where ammonia comes in contact with water and creates hydroxide. The only downside or fault in this definition is ammonia is a base. See, it does form hydroxide, which would make the solution basic, right? But it doesn't have a hydroxide in its equation. That's where this definition of acids and bases falls flat in its face a little bit, and that's why in the next video I will show a better definition. But this one works as a very simple, very basic definition. So the goal of this lesson is to understand the difference between these two definitions of acids and bases. You learned the Arrhenius definition in the last video, but that's something more like grade 10, 11. The more grade 12 and university definition of acids and bases is called the Bronsted-Lowry definition of acids and bases. So in this, acids are proton donors, meaning they will donate hydrogen cations, which are essentially just protons. And one way I memorize this is, I think, acidic, right? And I break up the word acid-ic. Ic meaning like as if it was disgusted by hydrogen and wants to get rid of it. Ew, ic, right? A base in this definition is proton acceptors. So they will accept hydrogen cations. The only thing to memorize is bases in this definition must have a lone pair. So they could be like a bench shape, and like according to Vesper, or seesaw, another Vesper shape, or just the E value is greater than 0. And what this does is ammonia and hydrogen fluoride, those are bases that weren't included in the Arrhenius definition, but they are in this one. So that's the big improvement of this definition. So if you remember from previous units, an equilibrium equation is an equation that goes back and forth until it finally finds a place to settle at, or an equilibrium to stay at. It's represented by, or indicated by, this symbol here. Now in this equilibrium equation, ammonia is accepting a proton and becoming ammonium, meaning it was basic in nature. This water here lost or donated a hydrogen to become hydroxide, making it an acid, right? So the hydroxide is the conjugate base of water here, because it's sort of like the opposite, right? This is basic because it could accept the proton and come back to water. This is acidic because it can donate that proton to hydroxide and become ammonia again, right? Because in equilibrium equation it goes back and forth. Now use that information and try and solve this question. Label which one is the base, which one is the acid, which one's the conjugate base, and which one's the conjugate acid. Now, if you pause the video and finished it, that's great. I'll do it myself now. They're both the same, they're both water. So this could be the base, and it accepts a proton and becomes hydronium here, making this its conjugate acid. This has to be the acid, right? And it loses or donates a proton to become hydroxide, meaning this is the conjugate base of this acid. Notice how water can both be an acid and a base at the same time? Well, that's why when you do a pH scale, water is directly in the middle. It's neutral, right? And that's because this reaction happens often, right? This is just due to hydrogen bonding between water molecules, as you learned in the first unit in grade 12 science, or sorry, grade 12 chemistry. And the hydronium and hydroxide form kind of cancel out the basic nature and the acidic nature. So it has properties of something that is neutral, that it's nullified in a sense. That's what makes water the universal solvent that you hear it, called a lot.
A strong acid or base fully dissociates in water, while a weak acid or base partially dissociates in water. If this represented a strong acid, then it would be the limiting reagent in this reaction, and it would fully react to form as much product as possible. Same thing if this were a strong base, then it would fully react to make as much product as possible. If these were weak acids or bases, then only a small amount would turn into product, while the rest stay as the compound they originally were. An easy way to remember this is a strong acid or base always finishes the race, as if the strong acid always crosses the finish line and always fully reacts in water, while a weak acid or base can't make it so far. Now, the reason why this information is useful is, let's say if you were in the manufacturing industry and there was a acid spill, and you do not want to put a strong base, or at least too much of it, because if you go over the amount required to neutralize the acid, then now you have a strong base on your hand, which is very potent because it would fully react with water and have its basic properties be very pronounced. And you don't want that happening. So you have to understand what kind of strong bases, what kind of strong acids can you use, or even weak or acids or bases you can use for cleaning or neutralizing an acid or base spill.
If you were asked to find the hydrogen ion concentration or the H3O concentration, they're the same thing, of 0.1 moles per liter of nitric acid, it's actually very simple. Nitric acid is a strong acid, and therefore, since it fully dissociates in water, the concentration of that strong acid is equal to the concentration of H plus ions or H3O ions. So the answer to this question is actually just 0.1 moles per liter. Now, if you wanted to find out the hydroxide concentration of 0.1 moles per liter of calcium hydroxide, which is a strong base, then you have to use this equation. The concentration of a strong base is equal to the concentration of hydroxide. So I want you to pause the video and just think of what the answer could be. And if you got this answer, 0.1 moles per liter, again, you'd be right. And this is because, again, a strong base and a strong acid fully dissociate in water. And if you wanted to find out the opposite, so let's say the question was asking you was the hydroxide concentration of a strong acid like nitric acid, and you knew nitric acid's concentration, then you could just put it in this equation and solve. This equation right here has the ion product constant set as equal to the concentration of hydroxide times the concentration of hydronium, or in other words, the concentration of the H plus ion. This constant is equal to 0.0 times 10 to the power of negative 14. And let's say you wanted to solve for the hydroxide concentration of 0.1 moles per liter of nitric acid. You simply just plug in the values and solve. And for this question specifically, you'd get 1 times 10 to the power of negative 13 moles per liter as the concentration of hydroxide for 0.1 moles per liter of nitric acid. Danish chemist S.P.L. Sorensen came up with the pH scale using logarithms. And logarithms just make big numbers small, so that way scientists don't have to put 7-digit, 8-digit numbers on their research papers because that takes up a lot of space. On log scales, the difference between 6 and 7, at least if it's in log base 10, it would be times 10 instead of just a difference of plus 1. And the difference between 5 and 7, rather than being a difference of plus 2, the difference is times 100. It's kind of like rolling a snowball down a hill, and it'll just keep getting bigger and more massive, like exponentially so. So if you wanted to calculate the pH of a solution that has a hydronium concentration of 0.1 moles per liter, well, you just use this equation. pH is equal to the negative log of the concentration of hydronium. And I want you to pause the video and try that out. So if you pause the video and tried it, basically what you had to do if you did it right is you put in negative log, base 10 of course, of 0.1 moles per liter, which is the concentration, and you'd get 1. The answer should be 1, which is a very acidic solution, which you must have learned how the pH scale kind of works. The left end is very acidic, and while the right end is very basic. And the pH scale is ridiculously important. The Canadian government has a whole research team dedicated to testing the pH of our water, because the pH of the water can affect the health of our skin, our eyes, our teeth, our hair, and even our diet in good and bad ways. So they have to make sure it stays at a relatively neutral pH level. This question is from the textbook, and I encourage you to pause the video and read over so you know what's going on. But basically, it's asking us to find the percent ionization and the ionization dissociation constant using the concentration of a solution and the pH of that solution as well. So first, set up an ICE table, which is something we learned in a previous unit, the equilibrium unit, and that helps us define the change in concentration represented by X, and that value is just the concentration at equilibrium of either this anion or hydronium. And what's useful about this is if we can find that concentration, we can calculate for the constant, which is the concentration of the products divided by the concentration of the acid here, not including the water, because the water is assumed constant because there's abundance of it. And the first step, since we have the pH, we can solve for the concentration of hydronium using the pH calculation from the previous, the pH equation from the previous video, and using a little bit of equation solving and then rules of logarithms, you can find that the concentration of hydronium is equal to 3.16 times 10 to the power of negative 3 moles per liter. Once you plug that into the equation, so you sub that in for the two concentrations on top, because that is essentially just the concentration of these two. Basically, these two are they're equal. The concentration is equal, so you could put them both at the top. And then the concentration of the acid at equilibrium is 0.10 moles per liter, which was the molarity we were given originally minus the moles per liter or molarity we have now. And then once you solve, just go through with the arithmetic here, and then you will get 1.03 times 10 to the power of negative 4 as the constant. And to find the percent ionization, which is really simple, you just put the dissociated concentration divided by the initial concentration of the acid that reacted, and then times it by 100%, and you will get 3.16% for this equation. This question specifically, and that's it. There's a lot of moving parts here, but once you understand and you know your math, you're pretty good. So salts can actually have neutral, acidic, or basic properties. A salt is an ionic compound formed from a neutralization reaction. As you learned, it is the reaction between an acid and a base forming a salt and water. Salt, like sodium chloride, is actually neutral in solution, meaning water will actually surround both the ions once it dissociates in the water, forming the sodium and the chloride ion, and the water will just surround them, and nothing will really happen, right? There's no acidic or basic properties there. But something like ammonium nitrate is actually acidic, and it'll create hydronium in water. And potassium cyanide is basic, and this will create hydroxide in water once it dissociates. So That's how salts can actually have acidic or basic or even neutral properties. This is my simplified method of predicting whether a neutral, acidic, or basic salt will form. A strong acid and a strong base will make a neutral salt. A strong acid and a weak base will make an acidic salt. A weak acid and a weak base will make a basic salt. And knowing these properties of salts is actually super useful if you go into industrial medical chemistry. These guys make antacids, which are basically just a basic solution you drink to neutralize stomach acids that are causing an upset stomach. And a good example of this is calcium carbonate, which is not a base, but it has basic properties as a salt. So instead of using a base, they can use a salt called calcium carbonate and fix your upset stomach. The definition of titration comes from the French chemist Joseph Gay-Lussac. And when we're doing acid-base titrations, basically what we're doing is we're just causing a neutralization reaction to occur, and then we're using that information to find the unknown concentration of a solution that we don't know the concentration of. So the way we set this up is we get a burette and we fill it with titrant. And titrant is either an acid or base that will react with whatever is in the flask, a solution that is either an acid or base that needs to be neutralized. In the flask, you put in an indicator, so when the reaction fully goes through, you'll know when it happens because the color will change. You'll turn this knob, and then the titrant will slowly be dripped into the flask, and then it's up to you to watch for it to fully change color, and then once that happens, you switch the knob, and you start doing calculations. So in order to do the calculations, you just use a simple dilution equation that an easy way to summarize is on the left side for concentration 1 and volume 1 is whatever information of the solution in the flask is. So you don't know the concentration, but you do know the original volume because you measured it to put it in the flask. And for the burette, which is whatever was in the tube, or this tube looking thing here, you put the concentration of that because you knew it, and then you put the volume that you used. One thing to note is the titrant, you know all the information about. You know what the concentration is, you know what the volume is, you know what kind of chemical it is. But for whatever is in the flask, you only know what kind of chemical it is and the volume, but you don't know what the concentration is, and that's the point of this reaction, or rather the point of this lab. And note that this is only for a 1-to-1 ratio. If there was 2 moles of titrant needed to neutralize 1 mole of solution in the flask, then you need to put a coefficient of 2 in here to have it as a 1-to-2 ratio. And that's basically what the purpose, the setup, and the calculations of titration are for acids and bases. Buffer solutions are solutions that resist change in pH. Kind of imagine your parents who are stuck in their old ways, and it's hard for you to go and convince them to do otherwise because they like where they're at. Same thing with buffers. And there's 2 examples of buffers I have here in our own blood that keeps our blood at a neutral pH level, keeping us alive. The first one is the phosphate buffer in blood. When a strong acid like hydrochloric acid donates a proton to the buffer solution, it's a weak base, and it'll accept that proton and become a weak acid. But if you think about it, it's actually the conjugate acid. And when the reverse happens to this weak acid, when a strong base like sodium hydroxide is added, it will, as an acid, it will donate that hydrogen to the hydroxide when this sodium hydroxide disassociates in the water, and it'll form that same weak base again, and it's like a push-pull. It's going back and forth, and it'll keep that pH at a consistent level, even though a very strong acid and a very strong base are added to it. Same thing with the bicarbonate carbonic acid buffer in blood. So sodium bicarbonate, when it's added when it reacts with the hydrochloric acid, which is a strong base, it will create a weak acid, which is the conjugate acid of this weak base here. And when this weak acid reacts with a strong base, like sodium hydroxide, it'll form sodium bicarbonate again, kind of starting the cycle. As I explained, it's like a push-pull. It will, go back and forth, but it won't allow the pH to be changed too much. And that's what buffers are, and they're really useful, and they keep us alive.